Hey everybody, welcome back to lesson 4.1. Today we're going to be talking about exponential functions. So exponential functions are any function that has the equation y equals b to the x, where b is some constant number that's positive, greater than 0, and not 1, because if we have y equals 1 to the x, well 1 to any power is just 1, so this is just y equals 1, which is just a flat line, so that's not going to be exponential. So there's two different kinds of exponential function. The first one is called exponential growth, and it happens when the base b is greater than 1. So for our example, we're going to say that b is 2. So consider the function y equals 2 to the power of x. So we're going to fill in our table. All right, well, anything to the power of 0 is going to be 1. So 2 to the 0 is going to be 1. 2 to the 1 is going to be just 2. 2 squared is going to be 4. And 2 cubed is going to be 8. When we look at our negative powers, remember that when we have a negative power, we flip it into the denominator. So 2 to the negative 1 is 1 over 2 to the 1, which is 1 half. 2 to the negative 2 is going to be 1 over 2 squared, which is 1 over 4. And then by the same process, we can get that 2 to the negative 3 is 1 over 8. Sorry for the interruption, there's just a fire drill. All right, so now that we have our table, we can sketch our graph. So let's plot our 0 first. So 0 is going to be 0, 1 here. At 1, we go to 2. At 2, we go to 4. And at 3, we go to 8. And then for the negatives, because our scale is so small, we're going to have to be a little bit approximate. But at negative 1, we're at about a half. For negative 2, a little bit closer to the y-axis at a fourth. And then it's really hard to draw an eighth on this scale, so we're just going to draw a dot, almost touching. All right, so now we're going to connect all these lines with a smooth curve. We're going to get a shape, something like that. Pretty good, if I do say so myself. So once you're done sketching, meet me at exercise 2. All right, so exercise 2 brings us to our second case, where the base is more than 0, because it has to be an exponential, but it's still less than 1. So 0, b is between 0 and 1. So our example here, instead of 2 to the x, is going to be 1 half to the x. So again, anything to the 0 is going to be 1, so we're going to fill in our table. 1 half to the first is going to be 1 half. 1 half squared is going to be 1 half times 1 half. It's going to be 1 fourth. And 1 half cubed is going to be 1 eighth. You can maybe see a pattern between this one and exercise 1. So if you want to take a minute to guess what the other three are going to be, feel free. All right, so to fill in our negative powers, we're going to remember that 1 half is really 2 to the negative 1. So if we're putting 2 to the negative 1 to the negative 1, our power to a power rule kicks in. We have 2 to the negative 1 times negative 1, which is just 2, 2 to the 1. So 2 to the negative 1 is going to be 2. 2 to the negative 2 is going to be 2 to the negative 1, the negative 2. It's going to work out to be 2 squared. It's going to be 4. And then 2 to the negative, 1 half to the negative 3, I'm sorry, is going to be 8. So these should all be powers of 1 half, not powers of 2. I'm sorry for any confusion. All right, so as you might have noticed, this is a mirror image of the one we had above. Instead of going from 1/8 to 8, we're going from 8 to 1/8. So our graph's going to look reflected across the y-axis. So at negative 3, we go up to 8, negative 2, 4. We go down negative 1, 2. We're going to cross at the same point, 0, 1. Then we have 1, 1 half, 2 comma 1/4, and 3 comma 1/8. We're going to connect all of these again with the smoothest line we can draw. And I'm sorry, it shouldn't curve up at the end. It should just keep going down. I'm just not a very talented artist. So make sure your line stays very, very flat at that point. Once you're done sketching your flat and or curvy line, meet me. Let's talk about asymptotes. So an asymptote is a line that a relation or function gets very close to, but never touches and never crosses. So our asymptote here is going to be at this pink line, which is y equals 0. Because if we look at both our graphs, this one, the green one's closer, so I'm going to use the green one. But if we look at it, it's getting very, very small, 1/8, 1/16, 1/32, 1/64th. But it's never going to be negative, because we're always multiplying 1/2 times whatever we had last time, so it's always going to be positive. But it's going to get smaller and smaller and closer to 0, but it's never going to touch 0. It's never going to cross into the negative. So it approaches y equals 0, but never touches it. So we call that line y equals 0 an asymptote. And unless we do some translation, which we're going to talk about in a second, our asymptotes are always going to be at y equals 0. You can change that with some translation, which we're going to talk about, I believe, now. Yeah. All right. So actually, in one exercise. So based on the graphs and behavior you saw on the previous page and recreated on the right, state the domain and range for an exponential function of the form y equals b to the power of x. So our domain is our set of x's. What are the x's that this works for? Well, all of them, right? There's no x value where b to the x is going to not work. We can always raise b to some power, right? So our domain is going to be negative infinity to infinity. Remember, we only have problems with our domain when we have the square root of a negative number or when we have dividing by 0, and neither of those are possible when we have a positive number to a power. So we're not going to have any problems with the domain, and the domain is supposed to be the entire set of real numbers, the whole number line. Our range is a little more interesting because we're going up to positive infinity on both these graphs, right? So our upper limit is going to be infinity. But as we discussed about our asymptote, our lower limit is going to be 0. We're never going to be negative, and we're also never going to equal 0. The lowest we can go is to approach 0 but not touch it. So we're actually going to use a parenthesis instead of a bracket because we don't want to include 0. There's no power you can put 2 to or 1/2 to that's going to equal 0. You can just get really, really close. So here we're going to talk again about the two different kinds of exponential function. So when b is more than 0, we have an increasing exponential function, which we call exponential growth. When b is between 0 and 1, we have a decreasing exponential function, which we call decay. For some application problems that we'll talk about. That's why we call it that. Okay. So exercise 4 asks, are exponential functions 1 to 1? How can we tell? What does it tell you about their inverses? So if you recall, the way we test if a function is 1 to 1 is to use the horizontal line test. So I'm going to draw a horizontal line. And you can use your finger or a ruler or the edge of a piece of paper. And we're going to drag it up and down the green graph. We're going to see if it ever touches more than once. Once, once, once. And even as it gets really, really flat, it never touches more than once. We can do the same to the red. And again, it never touches more than once. So that means that our exponential function, y equals b to the x, passes the horizontal line test, the HLT. which makes it 1 to 1. And if you recall, being 1 to 1 means that its inverse is also a function. We don't know what it is yet, but we're going to talk about it in a couple lessons. All right, so now we're going to consider the function y equals 7 times 3 to the x. And remember we have PEMDAS, so exponents come before PEMDAS. Exponents come before multiplication. So we're going to do our multiplying by 7 after we raise 3 to the power. So remember that it's not the same as 21 to the x. Just be careful you raise to a power before you multiply by 7. All right. So is this increasing or decreasing? Explain. All right, well, if we look above, when b is greater than 0, we have an increasing function. All right, well, what's my b? What am I raising to the power of x? That's going to be my 3. So since 3 is greater than 1, so this is increasing. All right, now we're going to sketch, labeling the y-intercept. Right, so to find the y-intercept, we just plug in at 0, so 7 times 3 to the power of 0. 3 to the power of 0 is 1. We have 7 times 1, which is, of course, 7. So our y-intercept is going to be 7. And we're going to use the same basic shape as we did up here. We have an asymptote at 0 because we didn't translate it at all. We didn't add or subtract anything. And it's going to be increasing. So something like this shape. And then it goes on in this direction as well. It doesn't have to be perfect, it's just a sketch. Sketch means you don't have to put any real scales on there. You're trying to get the general shape. When you're ready, meet me at exercise 6. All right, here's where we get to translation. This is when our asymptote may not be at 0. So our function here is y equals 1/3 to the power of x plus 4. So how does this function's graph compare to that of y equals 1/3 to the power of x? Well, like I've been hinting for a little while now, this has been translated up upwards 4 units. We took all of our y values here, we just added 4, we bumped them up. All right, so what is the asymptote at y-intercept of our pre-translation function, y equals 1/3 to the x? All right, well, before we do any translation, our asymptote is going to be y equals 0. So asymptote, before we translate, it's always going to be y equals 0. And at y-intercept, we plug in, and we get 1/3 to the 0 equals 1, because anything to the power of 0 is 1. All right, so our asymptote is 0, and our y-intercept is 1. Okay, so once we translate, what is our asymptote and y-intercept? All right, so once we bump up everything, our asymptote goes from y equals 0 and hops on up to, sorry about that. Our asymptote goes from y equals 0 and hops on up to y equals 4. And our y-intercept goes from 1 plus 4 to 5. So if we then sketch our graph, we're going to have an asymptote at y equals 4. We're going to touch, oh, sorry, this is going to be a decay. Sorry about that. So it has to be going downwards, decreasing, because our b is less than, b is 1/3, which is less than 1. So we're actually decreasing, and it's going to look something like that. So it's decreasing because our b is less than 1/3. It touches the y-axis at the y-axis, y-intercept is 5. We have an asymptote at y equals 4. If you've been instructed to, go ahead and do your independent practice. So asymptote is y equals 4, and our y-intercept is 5. Sorry. If you've been instructed to, do the independent practice, and until we see you next, make good choices.